Hey everybody, this is Mr. Bergman here. First of all, I want to congratulate you on finishing chapter one, which you can think of as kind of a toolkit for analyzing functions. So many of the ideas and the skills in chapter one are going to just resurface over and over again in my class, and then also the next class, pre-calculus, and the next class after that, calculus. So much so that I've summarized them into what I'm calling full graphical analysis. So every time I assign a project, and that's going to be like 9 times throughout the school year, there will be a graph, and I'd like you to perform full graphical analysis on that graph. And I'll show you what that looks like. Secondly, I want to also teach you some helpful tips and tricks for communicating the STEM world. When I say STEM, I mean science, technology, engineering, and mathematics. So I've had to give more than a couple STEM presentations in college and afterwards, and I'm going to show you how at least I communicate complicated technical concepts clearly in the STEM field. And I want you to practice and learn this in my class so that you too can communicate clearly in the genre of STEM presentations. Let me show you what I mean with an example. Um, this is an example of a graph that you could have to analyze, and so we'll do a full graphical analysis on this. And this won't apply in chapter one, but in chapter two, we're going to be producing these graphs by connecting the dots from data points. So you'll have like I will be giving you individual points, and then you have to like connect them all into a curve. And I'll show you how to do that later. But for now, just know that starting in chapter two, you'll have to analyze the whole graph and not the individual data points that I gave you. So the first big category is just tests, intervals, and transformations. So you have to report what the domain is, and you get the domain by collecting all the x values and putting them in interval notation from left to right. The range you also have to report, and you get them from collecting all the y values, again from bottom to top. And you can see here, this on the left is interval notation. It goes from negative infinity comma to the number that you see there, and with a bracket, and then and we'll just want I'm mostly highlighting that right now because I wanted to contrast the difference between interval notation and something that looks very similar to it, which is x and y coordinates. On the graph, you see different numbers with parentheses, and so that's just naming the location of that one point. But the slide is really about the range, which is in interval notation on the left. Um, the vertical line test, you can see it passes because it has when you draw vertical lines, those vertical lines pass through at most one point. It fails the horizontal line test, and that means, and the vertical line test, because it passes, it means that it is a function and not some sort of generic relation. The horizontal line test, it fails that. Um, Horizontal line test fails, and so therefore you can see that, it fails because horizontal lines drawn go through more than one point. And so therefore it fails. And we know that this function, we can't consider this what we might call a one-to-one function. And in chapter 6, what that means is that the inverse will not be a function. You have to report where it's increasing. That means where the graph reading it from left to right is going up. And as you can see, it's in interval notation. And you have to tell us when it's decreasing as well. Reading the graph from left to right, where is it going down? Where is it continuous, meaning over what interval can you draw it with like one swoop of your pencil if you were drawing it on paper? And you have to talk about the transformations. And here on this particular graph, there's 3 different transformations. There's the A value, H value, and K value. And they have 3 different numbers. So you have to, as you can see, I'm labeling the A value as a vertical dilation, the H value as a horizontal shift, and the K value as a vertical shift. Excuse me. Okay, and then as you can see, the effects of those transformations are all also indicated by these arrows that I've overlaid on top. Special points and lines is the next category of full graphical analysis. And so um, I've labeled all the x-intercepts and the y-intercepts. You can see where they are, and it's just the x-intercept is where it intercepts the x-axis, and the y-intercept is where it intercepts the y-axis. Extrema, very important. This only has one maximum. It's at the vertex, whose coordinates I've labeled here. And if there were a minimum or any relative max or min, then I'd list that out as well. Is there symmetry, or is a line of symmetry? So you can see this has a line of symmetry. It is reflectional symmetry over the line that you can see right there, vertically graphed, and the arrow is pointing to it. So I'm going to say this is not an. If this line of symmetry were at x equals 0 along the y-axis, I would say that it is an even function. But because it's kind of shifted off to the right, it no longer has even functionality. You can also ask, does it have rotational symmetry, and what would the center of rotation be? And then on top of that, if you're thinking about this after chapter 7, if we're looking at this, remember you have to report any asymptotes, and in chapter 7 I'll explain what those are. Next big question is, what is outside the viewing window? We can see here where the graph is, but what happens afterwards? You can see they're kind of pointing downward, and they leave the viewing window in a downward fashion, but does it always continue that way? In this particular graph, you can say yes. As x approaches negative infinity, y approaches negative infinity to the left. And then as on the other side, it also leaves the viewing window. As x approaches positive infinity, y approaches negative infinity. Next question, where does Desmos mistakenly display a straight line because it is unable to calculate any curvature? So you can see here, I've actually zoomed in. You can tell I've zoomed in because the screenshot that I have includes the x and y values in gray to the left and to the bottom. And I've zoomed in. I've chosen to zoom in on the vertex. You can see it doesn't look like the vertex of a parabola that you saw from the previous. Like, this is the same graph, except this is way zoomed in on the vertex. And actually, if you go in and look at Desmos here, there's no change. If you click on all these points, they're all the same y value, 3.1555. Now that's a mistake. Desmos has mistakenly displayed a straight line because it is unable to calculate any curvature. I've just zoomed in far enough that at this point it can't really tell the difference between a straight line and a curve. And so it's your job to find. I want to say that there's nothing special about the vertex. I just chose to zoom in on that. You could have chosen actually any point and zoom in far enough and eventually get there. And I want you to show me that you can do that. And it's later on in later chapters, you won't actually need to zoom at all, or maybe even depending on what um, function you choose for the mystery function project. In chapter 1, there will be places where you don't even have to zoom in at all. You'll see on the home screen, oh wait, it looks like a straight line, but it's really not. And I want you to report those. If you're watching this presentation or reading this slideshow and you've completed chapter 6, then I want you to show me what the inverse is. I want you to do an equation, a table, and a graph, and a vertical line test for the inverse of your function. So in summary, here's what full graphical analysis looks like. And I've listed all the previous slides, 17 slides or so, what it would look like, and all the different things in a quick summary right here. And I hope you reference this throughout the year and take a look and see. So the style for the STEM presentation, what does it look like to do this well and to communicate technical concepts very clearly in the STEM field for STEM professors or STEM startup companies or wherever you find yourself communicating technical STEM stuff to STEM people? So first principle is say it, see it. If you're going to say heart, moon, face, then we want to see a heart, moon, and a face in your presentation. That's good. Don't say chair if we can't see a chair, and don't show us a box if you're not going to talk about it. So whatever we say, we also have to see. This applies to most of the big presentations and big ideas and big concepts and meaningful results. And there's one exception. I don't want you to recite or read aloud any numbers that have no units or meaning within the context of the research story you're telling. So there's actually a lot of these in full graphical analysis. You notice I didn't actually read out the numbers on the vertex, where the vertex is. You can see it. There's going to be plenty of numbers that do have units, that do have meaning in the research story that you're trying to communicate. But when it comes to full graphical analysis, if it's a number that has no real meaning in the context of the experiment that you're talking about and the research story you're trying to tell, then you don't. There's no point in reading the number. So instead, let the audience see the number only, and then offer a quick explanation of how you found it, which is what I did. Second, sentences. Please do write out their sentences and very precisely with the vocab that you have, and put them in the speaker notes. You notice there's no in the full graphical analysis that I did, there was no sentences typed out and just left on this screen for people to try and read and listen to at the same time. It's very distracting and difficult to do. Instead, cut and paste. So the big tip, as you can see in the top right, is to cut and paste from your slide into your speaker notes any sentences that you have, and that's what I've done. Now, I have quite a few sentences in my speaker notes that I'm reading right now, and you should deliver this concisely. A good STEM present. I know I'm not following this at all, but if you can keep your presentations down to 5 minutes, then that's best. Sorry, I'm not doing that here. I'll do better next time, I guess. So as you can, I'm going to read what it is on the right. Don't do what I'm doing now, which is writing out what I want to say word for word, verbatim onto the slides. It turns the whole thing into one of those um, kids sessions where the librarians read a book out loud in order to teach kids how to read. It's terrible. Don't do it. Third, format, clear and simple. On each slide, let there be just one idea and if you have to communicate a lot, then that means you're going to be making many slides. And the full graphical analysis that I went through, that had at least 17 slides on it. And there was one idea on each slide. And you're going through each slide kind of quickly, talking about all the different ideas you have. It's a very simple layout, only a title and a picture and a result and an arrow somehow helping us think about that result. The numbers should be rounded, and if there are any units, then you take every opportunity you have to label a number with a unit. The full graphical analysis example that I had no units because it's just a graph. But once you start telling stories about data, then you have to take the opportunities that you have to label those numbers with units. And the graphs, lastly, have got to be really well zoomed, and so we can see the axis, we can see where it is on the graph. So here I'm going to break all those rules right now with this slide. Check this out. This is what you want to avoid. First of all, it's super crowded, right? There's like 1, 2, 3, 4, 5, 6, 7, at least 7 different results, all on the same slide, and it's just not good. Then you could see the numbers that I hear. If I really wanted to bore you, I could say the range is -infinity, comma 3.15648393845784853. Oh my gosh, end it. No. Please don't recite your numbers. We can read the numbers if we need them. The exception of that would be if you are reporting a significant result. Then you can say, look, I've got 15 camels here. I've got 4 viruses, whatever it is. Don't recite the numbers unless they're super significant and a result you want to report within like if you're answering a central question, for example. Also, the numbers here are not rounded. They're too precise. It's indicating a certain level of precision that you just don't have, and it's boring too. And they have no units. Um, the graph itself, look at the picture of the graph. It's terribly zoomed. There's no axis. I can't tell where this this parabola is. I have no idea. I just can't read it. I have no context. And there's so much white space over here. Like, look at all this. And the little red graph only occupies like the bottom quarter left, the bottom left corner of the graph, and there's all that other white space. It's terribly zoomed. There's no axis. I just can't read it. And there's no arrows to indicate how we should be thinking about this graph. So that's what I wanted to say. Please avoid these mistakes. And next, I'll teach you how to tell a research story, but we'll say that for some other time. Thanks. Take care. And I can't wait to see you in class.